So cracks can tell us a lot of information about the hidden story of concrete. They can tell us ideas about its safety, performance, and longevity. But the question is, how well are we listening to concrete? So instead of looking at cracks as a sign of damage, we propose seeing them as a source of data-rich information, which can proactively guide infrastructure management decisions. Good afternoon, everyone. My name is Majdi, Flah. I'm working at the Civil Engineering Department at McMaster with Professor Majdi. So today I'll be talking on how we can use deep learning to quantify cracks, learn from the patterns, investigate their different orientations, and finally, its implications on the structural integrity. First of all, I'm going to start with an introduction, talk about the problem statement, the methodology adopted, the results, limitations, the main novelties and contributions, and then I'll talk about the future research which is going to make the AI recommendation repair. And finally, we will conclude this work. So I see that most of the research is basically focused on developing innovative concrete mixes. But what's going to happen about that building or that bridge that we can't really demolish? So when the structure is very important, too expensive, or too embedded, as we can see, most of the buildings and most of the bridges were built in the 1960s, 1970s with a service life of 50 or 75 years. So we are basically nearing the end of these important structures. So all of them are aging, and none can be destroyed, and all must be repaired sustainably. I think that everybody is talking about sustainability, but we are talking about it from a formulation point of view. How about repair? So we will move to the problem statement. So none of us can deny that the situation of our infrastructure is getting worse and worse. Whether buildings, bridges, dams, or any other civil engineering structures. In a report published in 2017 by ASCE, they said that the condition of their bridges is marked as C+ on a scale from A to F, where A corresponds to the excellent condition, and A and F corresponds to the lowest case scenario. So more than 185,000 bridges are in need for urgent consideration. Over 46,000 of them are nearing the end of their service life. So the budget for retrofitting was set at that time in 2017 to be $123 billion. So you can imagine what's going to be the number in 2025 with climate change and a lot of issues and temperature variations, and concrete depends on the environment. I'm here comparing between two different scenarios for a new building and a retrofit. So the quantities here assume a 10,000 meter square building with a lifetime of 20 years, and as you can see, we can easily save 600 kilograms of CO2 equivalent per meter squared through reuse. And the red color basically talks about the embodied carbon, and it's mostly due to concrete. So let's talk about the inspection protocols. Usually, we send our inspectors to the site to look at the damage, look at the cracks, and subjectively try to determine what's happening in the crack. Is it safe? Is it within the limits? Is it less than 0.3 millimeter, as we have in the Ontario inspection manual, for example? So this kind of inspection is very dangerous, time-consuming, repetitive, and subjective. So the question now, how can we repair this sustainably? Thanks to the advances of sensors and drones and all the IoT things and machine learning and all that, we now have the accessibility to use drones. They are time efficient, data-driven, performance-based, and cost-saving. Now, how can we use that? So computer vision has a set of successful records dealing with other applications, like, for example, the autonomous vehicles, health applications, facial recognitions. So this drone is going to take a big database of images, and then instead of feeding that to our most highly inspector, we're going to give it to the deep learning algorithm now. And this can be done in a matter of seconds, instead of spending days and months doing such a repetitive task. Let's talk about the methodology. So first of all, given the success of the deep learning framework, I want to develop that for crack detection, for civil engineering applications. Second, do we need to stop at classification? Or can we go for further applications like shear, detecting the cause of the crack? Is it shear, flexural, combined, or durability related? Like, for example, corrosion, bond damage, and other kind of applications. And finally, I don't want to stop here. I also want to quantify the crack in terms of the length, width, and the angle of orientation, and that's going to serve us to determine the cause of the crack. So first of all, I got the data that's publicly available by Middle East Technical University in Turkey. It's publicly available. They took 458 images with high resolutions, and then I had to crop them to 227 by 227 in terms of the number of pixels and the x-axis and the y-axis. And 20,000 of this data is basically containing cracks, and the other doesn't have any crack in it. So the surface is intact, and there is no problem in terms of durability or structural, deterioration. Now, I want to pre-process the data. So first of all, I'm going to clean any kind of distortions, blurriness, low resolution, and if the data contain any of that, so basically I'm going to remove it. And finally, I'm going to be left with 10,000 images, 5,000 for cracked and 5,000 for not cracked, and then I'm going to perform all the operations in order to get the best quality of images that I can train my deep learning algorithm on. So I have 3 different classifiers. So the first classifier will just basically predict if it contains a crack or not, and then 2 other classifiers will predict the orientation of the crack. So if the crack is coming in a vertical left orientation, vertical right orientation, horizontal or vertical, so I need to basically feed this information to the algorithm so it can predict the cause of damage. So this is the mechanism of our study. So we're going to send our inspector. He's going to look at the structure using a drone, and then we're going to feed it to the deep learning algorithm, or I have it here as convolutional neural network. So that neural network is going to predict, first of all, if we have any crack or not. If we have a crack, we're going to go to the image quantification using the Otsu image processing, and then we're going to start the work. We're going to start with quantification of the crack, damage severity, and then finally the failure mode. So these are some of the steps of the image segmentation. First of all, we're going to start with improving the image. As you can see, moving from this side to the other side. This is how the crack looks like in the beginning. And then we're going to start processing the crack, improving the image, thresholding, noise removal, and finally we're going to have a very clean black and white crack where we're going to operate all the operations of crack quantification there. So here, how the crack looks like. First of all, I'm going to determine the length based on a MATLAB algorithm. I'm going to try to determine, basically based on the number of pixels. In the x-axis and the y-axis, I'm going to determine the maximum distance between all of these points, as you can see there. We have DAB, AC, AD, BC, and BD, and then I'm going to try to get the maximum of all of these distances, which corresponds to the length. And then I'm going to operate and get the width of the crack, and finally the angle of orientation. So the main results of our algorithm, we have up to 96% of accuracy, and this tells basically that we are predicting the right orientation of the crack, or if we have a crack or not. So if we have a crack, then basically the algorithm is going to say, yes, we have a crack. If we don't have it, then the algorithm will state that as well. Not only that, but also we're going to predict the orientation of the crack exactly, where it's coming, how we labeled the crack in the beginning in the training process. And the loss is only 0.14, just to give you a background about the loss. So loss, the closer to zero, the better it is. So these are the validations on, we conducted like at the university some operations. We went to different sites and we tried like to capture some realistic images from the field. And as you can see that, for example, the length error was about 1.5%, the width error was about 5%, and the angle error was about 2%. So nothing is perfect. We have limitations. So first of all, our algorithm is perfect at predicting one single crack in the image. But the real life scenario is very far from that, right? We have maybe some intersecting images, or maybe we have some, as you can see here, for example, this is one of the limitations. We have two cracks that are parallel. The algorithm in here will just predict and quantify the widest crack. This is the first limitation of this algorithm. The second limitation is that if we have two different cracks that are intersecting, the algorithm is going to quantify the widest crack. As you can see here, we're quantifying from here up to here. All this one is going to be the cracked part of concrete. And, of course, since we are sending a drone for like structures that are hampered by demanding access. So in this case, we have to be careful about the lighting conditions. If it's a foggy day, for example, then we cannot really send our drone to do any inspection. It has to be within perfect lighting conditions. So what is the novelty and contributions of this work? First of all, we demonstrated that a precise quantification of cracks is essential for effective structural health monitoring. We provided a new configuration of the deep learning architecture, and then we provided at the end a nearly automated inspection platform. We don't want to say automated because we still have a lot of, back and forth discussions between the inspector and the operator of this algorithm. Now let's talk about what we want to do for future. So as you can see, we just completed the two first steps. Our vision is for an AI repair recommendation output. So at the end, we want to send the inspector, but at the same time, instead of sending him, we're going to give him a set of solutions. 10, 20, 25 different scenarios that correspond to the best case scenario. So first of all, we're going to start with the images, and two of these steps are already done. Now we are already at the third step, and we still have, like, for example, exposure and context mapping, functional repair requirements, material filtering. So basically, instead of just providing an OPC mortar, we're gonna tell the inspector, basically, and the algorithm what kind of functionality of repair we need, depending on the environment, depending on a lot of different ideas, and depending on some information about, about the structure itself that we are trying to monitor. So for example, in this case, you can see we have a frame, and we are trying to guide the algorithm. If you see at crack A, so these two cracks are basically more or less related to durability. It is more of a chloride attack or a bond damage. Same thing for B. But if we look at D or C or F, these cracks are mostly structural. They depend on the orientation, they depend on, and that's why basically we're gonna use that orientation of the crack to quantify at the end, like the reason or the creation cause for the algorithm. Cracks don't happen only because of structural limitations. If we have a structural problem, then that's a big problem. But they're mainly related to durability. So we need to have an information about where exactly we are inspecting the structure. If we are inspecting it, for example, within northern Canada, where we have a lot of freeze and thaw cycles, or we are inspecting it in Toronto or Montreal with a central region, or high CO2 atmospheric problems, a lot of temperature variations, and it depends on the area exactly where we are doing and where we are conducting the inspection. So this is what we call performance-based repair. Instead of going for general repairs that can go everywhere, if we want to really go for sustainability, I think this is the solution. So here we are narrowing down basically the reasons of creation of cracks, why exactly the cracks are happening. So given the information about the failure type and the exposure risk, depending on the durability and the location where exactly we are inspecting the structure, we can feed a lot of information to the model. For example, for durability, what are the durability requirements? Do we need an impermeable, or how about the frost resistance? How about the thermal compatibility of the repair we are conducting? And then for structural, do we have fatigue? Are we conducting an inspection for a bridge or a building, or depending on the load that's applied on the structure? And then same thing for serviceability, constructability, and then finally, and most importantly, and this is main part of my research, is to find alternative solutions on how we can cut CO2 emissions. So at the end, we're going to have such a form of a mixer, you know. We're going to have a lot of different trade-offs, we're going to have a lot of different objectives, and we want to provide a trade-off, what's going to be the best solution depending on the context we are in. And then we will identify optimal mix designs depending on the environment, and then at the end we're going to apply multi-criteria decision-making. Just to give an idea, for example, we have this example here in that table. We have 3 different alternatives. We have, for example, slag mortar, RC3 grout, or OPC patch. We are going to look at the bond, the CO2 emissions, the life expectancy, the cost, and then we're going to provide like a list of ranked solutions. And then it totally depends on the inspector to pick the best solution they think. So, concluding this work, we provided a deep learning model that's combined with image processing techniques that accurately classifies and quantifies various crack patterns and damages. We are calling to go for repair instead of just focusing on building new structures. It's the time to focus on repair. And finally, we are providing NAI-driven repair solutions that can offer optimized and context-sensitive recommendations, or what we call the performance-based repair, instead of just generating the prescriptive type of repairs we usually provide.